Hello all, and welcome to the Chinese remainder theorem video. So before we jump into it, I actually want to sort of demonstrate how the Chinese remainder theorem works in terms of like a really cool visual modular arithmetic example. For those of you maybe a little rusty with modular arithmetic or who just want a cool, more visual understanding, I think this will really help you out. And when I go into the full math of why it works, I think you'll be able to sort of recall this as opposed to me just shouting mod at you a bunch of times. So I have 8 cards total. I've got 4 spades, 4 hearts. And if you'll notice, we call this the reflection. The hearts are sort of reflected or mirror image of the spades over here. You could also think this is like a flip. So if I took these cards in my hand and I just flipped them over, they would all line up really nicely with the spades. So we're going to have a game with 2 rocks. I'm going to have a yellow rock on the top here and a purple rock on the top here. And these rocks can only move in a clockwise fashion around like this, and they can only move 1 square at a time. And what I want is a number of total moves. So 1, 2, 3 is the total moves, or 1, 2, 3, and 4, 5, 6. That's the total number of moves. And I want a total number of moves where the card that the stone lands on for both groups is the same card. So one solution to these this group of 4 cards is 3. So if we go 1, 2, 3, we get 2. Doesn't have to always be 2. We can get the ace by just going 1, 2, 3. And so yeah, where the game gets sort of a little more challenging and the math gets a little more challenging is what happens if I remove 2 of the cards and I have these guys right here, and I still want that same number to work for my 3 group now. But if you'll notice, 1, 2, 3, that just takes us back to 4. And then I, in fact, also want it to work for if I just have 2 cards, and I also want it to work if I just have 1 card. All right, so let's put these cards in the proper order so we don't have to start again. And the Chinese remainder theorem is able to solve this problem for us, and it gives us a lovely 11. So let's test it out. 2 numbers that add up to 11. So we'll just start with this side, and we'll just start counting. 1, 2, 3, 4. But you'll notice something a little interesting is that once we have 4, we go right back to the start. And any 2 numbers that add up to 11, one of them is going to be greater than or equal to 4. So we can sort of use this as a strategy to start to understand things. So we just moved 4. What do we have left over? Well, we've got 7 more moves to go. But hold on a minute. 2 numbers that add up to 7, one of those is also going to have to be greater than or equal to 4. So let's move another 4. 1, 2, 3, 4. Reminder that it doesn't matter which side we do because we're always going to end up at the same spot. So we've just moved a total of 8 times. We do a little quick math. 11 minus 8, we end up with 3. And if you'll remember, 1, 2, 3 was the solution to our 4 puzzle. So now let's put the rocks back and let's take out the 2s. All right, so bring this back into focus. Let's try 11 again, but let's try it with this new sort of mindset where 2 numbers that add up to 11, well, not only will one of them have to be greater than or equal to 2, one of them is going to have to be greater than or equal to 6, which is 2 3s. So let's try this out. 1, 2, 3, 4, 5, 6. Just a reminder, it doesn't matter which one we do because we're going to end up at the same spot. And what do we have left over? We've got 5 left over. 5 possible moves. 2 numbers that add up to 5. One of them is going to have to be greater than or equal to 3. So we can make another 3 moves. 1, 2, 3. And what's 5 minus 3? Right now we're down to 2 more possible moves. And if you notice, if I go 1, 2, I end up back at the ace. Or if I only just do one move, I end up at the 3. And finally, let's take these 3s out. And 2's a little funny because actually any odd number works. If you think about doing 1, we get 4. If you want to do 1, 2, 3, you get the ace. If you want to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we get the 4s. But also we can think about it in terms of multiples of 2 numbers that add up to 11. One of them is going to be greater than or equal to 2, and we can keep going all the way down until we get that same result of a 1 remainder. Or if you like to think about, there's 5 2's here, right? Because we can get to 10. So we do this 5 times, and then we're back here, and then we do this 1 time, and we get the same number. So I hope you guys enjoyed this little explanation of the Chinese remainder theorem. But now let's get into the nitty-gritty math. Hello, everyone, and welcome to the Chinese remainder theorem. So, the Chinese remainder theorem states that there are certain things whose number is unknown. If we count by 3's, we have 2 left over. If we count by 5's, we have 3 left over. And if we count by 7's, we have 2 left over. This raises the question, how many things do we have? This is a math riddle / math problem posed by a man by the name of Sun Tzu in 3rd century China. Many of you may be thinking, is this the same guy that wrote The Art of War? And you are wrong, but it is his student, supposedly. So I guess they shared the same name. That part of history is a little out of my comfort zone, but it seems quite interesting. So this is a math riddle, and it certainly is a math riddle because, I mean, we have certain things whose number is unknown. We have leftover. We have how many things. Everything about this screams difficult problem to solve. And sure enough, what we get when we put it into sort of math language is that we have one unknown, x, that is congruent to 2 mod 3. That's like saying when we count by 3's, we have 2 left over. We have x is also congruent to 3 mod 5. When we count by 5's, we have 3 left over. And x is congruent to 2 mod 7. That's when we count by 7's, we have 2 left over. So that's a standard Chinese remainder theorem problem. And so what does the Chinese remainder theorem do? The Chinese remainder theorem can be used to solve a system of congruence equations. That's what this is, just up here. Congruence equation with one variable, that's our x, and at least 2 different coprime moduli. So what are coprime moduli? So 2 numbers that are coprime, we have a, b in the positive integers whose greatest common factor is 1. So an example is 16 and 9 are coprime since they share no factors greater than 1. So 16 can be broken up into 2 and yet another 2 and one more 2. And 9 can be broken up into 3 and another 3. So 3 does not equal 2, so they share no common factors besides 1. And what are moduli? So modulus, mod n, is the number we use to sort of wrap around when counting, sort of like how a clock resets after reaching 12. If you remember from the cards, we had 4 cards. We went from one card to the other, to the other, to the other, and it took 4 moves for the stone to get all the way back to where it started. So another way of thinking about mods is if we have A is congruent to B mod n, then A equals B plus kn, where k is an integer, or A divided by n has a remainder of B. So let's figure out 11 mod equals congruent, to something mod 4. So we break this down into, that should be congruent. 11 equals some b plus some k times
4. Now, how I like to go about solving these is I like to count up in fours. So once I get to a number that's relatively close to 11, I'm going to stop counting. So we just go 4, we go 8, we can even count up one more, we go 12. It's a bit too much. So we'll go back to 8. So we have, that's 2 for k. So 2 times 4 plus b equals 11. What is 2 times 4? That's 8. 8 plus what gets us 11? That gets us a b of 3. So 11 is congruent to 3 mod 4. Cool. So how do we solve a Chinese remainder theorem problem? Well, we are given exactly what we had above. So 1x with several congruence equations. We have 2, 3, 2 as our remainders, and we have modulus 3, modulus 5, modulus 4, or 7. Something to note is that 3, 5, and 7 are all co-prime. This tells us that there does exist a solution. If we have something like mod 2, mod 4, and mod 8, and we have a bunch of different congruence equations here, there could be a solution, right? It's not like there isn't a number that satisfies all of this, especially if it's all 1, right? But if it's not all 1, we can't concretely say that there is a solution. So that's why we want them all to be co-prime. So here's the solution, and is ready. I'm gonna do this in one breath. X equals little a sub 1 times big M sub 1 times big M sub 1 inverse time plus little a sub 2 plus big M sub 2 or times big M sub 2 times big M sub 2 inverse plus little a sub 3 times big M sub 3 times big M sub 3 inverse mod big M. Okay, so what the heck does this mean? We need to do some assembly to actually get some concrete numbers for this, and to even figure out, well, I mean, what are these big M's? What are these big M inverses? Why is this one not subscripted? You don't know yet. I'm going to explain it to you. So for our A's, and this is why I've color coded everything, it's significantly easier to understand where everything is coming from if you remember this is the blue equation, this is the purple equation, and this is the green equation. So our A sub 1, or the blue A, is going to be what we have left over. So that's going to be our 2. That's where we get this 2 from. Our A sub 2 is going to be this 3, and then A sub 3 is going to be this 2. Now, these are little m's here, not the same as a big M. These are not the same. So the little m just means the modulus. So the modulus of the blue equation, M sub 1, is going to be 3. Of the purple equation, it's going to be 5. And of the green equation, the modulus was 7. So now we're going to use all of this to first get big M. Then we are going to get these smaller, or sorry, still big, but subscripted m's. And then finally, we're going to get these inverses. All right, so let's start off. Big M, super easy. We just get all 3 of these, multiply them together, and we get a nice juicy 105. That is going to be what modulus we are going to get our answer in. Fret not, this can always be simplified. So now we have our big M sub 1. That's going to be this big M divided by what our M sub 1 was, our little M sub 1. So that's going to be 105 divided by 3, which gets us 35. I like to think of it a little differently. I like to think of it as big M, and we just cross out this 3. And that's what we're doing. But to me, that makes better sense visually and mentally. So for big M sub 2, we have 105 divided by 5 this time. That's our M2. Same thing as just doing that, which gets us 3 times 7, which is 21. And finally, we have big M sub 3, which the little m was 7. So it's 105 over 7, which gets us 15, which is 3 times 5, or the same as just crossing out that 7. So let's follow this little arrow over here and talk about big M sub 1 inverse. So big M sub 1 inverse is what we call a multiplicative inverse. Essentially, we have a number and we multiply it by the inverse of that number, we want the multiplicative, or we want the multiplication identity, which is E, or 1 in this case. So we want a number that when we multiply it by our big M sub 1, gets us 1 in the modulus that we are in, little m, which is 3. So let's just go ahead and fill that out. And we have 35 times big M sub 1 inverse is congruent to 1 mod 3. So now let's put 35 into mod 3. So 35 equals some b plus some k times 3. Start counting up from 3s. I'm getting all the way to 30. And then I'm going to add one more. So we're at 3 times 11. That's 33. That's pretty close to 35. So let's say k is 11. That's 33 plus what? Plus 2 is 11. So 35 is congruent to 2. That's not a 5. It's congruent to 2 mod 3. So we get 2 times big M sub 1 inverse is congruent to 1 mod 3. Now, if we think about a number that, where is 2 on the sort of mod wheel of 3, right? 2 is right here, and we want a number that gets us right here. So I like to think of this in terms of clocks now. And so we're sort of just drawing extra arrows. Essentially, we want one number that's 2 spaces higher than 2. And conveniently, 2 multiplied by 2 gets us 4, which if you start here and you go 1, 2, 3, and then back to 4, that's going to be 4. So 2 times 2 is congruent to 1 mod 3. We've solved for the multiplicative inverse. If you remember, we wanted a number such that when we multiply it, it's congruent to the multiplicative inverse of the modulus that we are in. So 2 is going to be big M inverse. And now we're going to do that 2 more times. So strap in. Following the little maroon arrow down here, we get that big M sub 2, which was, if we remember, it was going to be 21 times big M inverse sub 2 is congruent to 1 mod 5. So let's think about 21 in terms of mod 5. 21 equals b times k, or b plus k times 5. I'm immediately thinking of 20, right? That's 4 5s. So then 20 plus what gets us 21? Looks like 1 is going to be what 21 is in mod 5. And this ends up being nice and easy because 1 times what gets us 1 in mod 5? That's just going to be 1 times 1. So our multiplicative inverse of 21 is 1. Coming on with the green arrow, we have our big M sub 3 times big M inverse sub 3 is congruent to 1 mod M. And if you remember from up here, our big M sub 3 was going to be 3 times 5, which is 15. 15 in mod 7, think about 14, that's just 2. And then 14 and 15, that's 1 away. So it's once again going to be 1, which makes this nice and easy because that's just 1 times 1 is congruent to 1 mod 7. Therefore, 1 is equal to the multiplicative inverse of 15 up here. So now we've gotten our M1 inverses, M2 inverses, and M3 inverses. We also got our big M from up here and our big M blue, pink, and green. So we're going to plug everything in. Here's our formula once again. We get that x is equal to 2 times 35 times 2 plus 3 times 21 times 1 plus 2 times 15 times 1 mod 105. All right. That gets us that x is equal to 140 plus 63 plus 30. And so these are all the things we got from the green equation, the purple equation, and the blue equation. Then simplifying, we get that x equals 233 mod 105. So now we just have to solve for x and k in this situation. So we get that 233 plus k times 105 gets us x. Counting up, let's say 105, it's still a little bit far away. Maybe let's do, 210. Okay, so 210 plus 2 plus what gets us 233? That's going to be 23. So x equals 23. Now we can check our answer. 23 is 2 mod 3, 23 is 3 mod 5, and 23 is 2 mod 7. This is what we wanted in the first place, and this makes everything really cool, really nice, and convenient. But you may still be asking, as I was once I got here, how? how did this work at all? So the proof is rather lengthy, but a really nice way to understand it is that x is congruent. If we, instead of having, what do we have, mod 105, instead of having mod 105, let's have mod 3, and let's just think about this in terms of mod 3, because this still should work. So what we get here is that this is the original equation from our solution, and what I want you guys to notice is that there's a 3 here, and then this 15 is 3 times 5. So any multiple of 3 in mod 3 is just going to be 0. So these simplify down to 0, and then what we're left with is just this 2, because this had no factors of 3 in it, and we essentially were able to design it in such a way that this was going to give us 2, because that was what we had as a remainder, and that's our a right here from before. So we get that x equals 2 mod 3. So let's generalize this and finish up here. So given that x is congruent to a sub 1 mod m sub 1, and x is congruent to a sub 2 mod m sub 2, we get our little dots, and we get that x is congruent to a sub n mod n sub n. So we'll try to do this in one breath, but here is the generalized formula. X is equal to a sub 1 times m sub 1 times m sub 1 inverse plus a sub 2 times m sub 2 times m sub 2 inverse plus ... a sub n times m sub n times m sub n inverse mod big M. All right, that's the Chinese remainder theorem.